This is AP Calculus AB, and in this video I'm going to talk about section 6.4, and that is the fundamental theorem of calculus. Now, the fundamental theorem of calculus has two parts, and we're going to talk about both of these parts. We'll actually talk about the second part first and then go back to the first part. But let me just show you what the fundamental theorem of calculus says. The first piece of this is actually the idea that a derivative and an integral are inverse operations. So when you look at that part of it, notice it says the derivative with respect to x of this integral from a to x of f of t dt is f of x. So essentially we're saying the derivative process and the integral process are inverse operations. And we'll go through some problems on that a little bit later and talk a little bit more about that. The second part of the fundamental theorem of calculus is actually the part that we use all the time when we're solving definite integrals. And in fact, we started using this in section 6.3 when we were solving definite integrals using antiderivatives. So notice what this says here. If f is continuous at every point of the interval a to b, and if f is any antiderivative of this function f on the interval from a to b, then this has to be true. The integral from a to b of f of x dx is equal to the antiderivative at b minus that same antiderivative at a. So notice it says any antiderivative. That's going to be really important, and I'm going to show you why that's the case here in just a second. So for this first example, let's take a look at the second part of the fundamental theorem of calculus, where we're talking about the idea of having a function that we're integrating and taking an antiderivative at the upper limit minus that same antiderivative at the lower limit. So let's talk about how that works and why it says any antiderivative. Okay, so let's say we have this velocity function, 1/2 t squared minus 2t plus 3 meters per second. And we have this position function, 1/6 t cubed minus t squared plus 3t minus 3/2. Notice that the position function is an antiderivative of the velocity function. So the first way we're going to solve this, it says solve the integral from 0 to 6 of v of t dt. And what does the result mean? So if I were to look at this integral from 0 to 6, v of t is 1/2 t squared minus 2t plus 3. And if I were to take the antiderivative of that, I would get 1/6 t cubed minus t squared plus 3t. And we would evaluate that from 0 to 6. Okay, so this is what we did back in section 6.3. Now, if I were to plug everything in here, what I'm going to end up with here is this is the same as 1/6 times 6 cubed minus 6 squared plus 3 times 6. So that's the upper limit minus the lower limit. When I plug in the lower limit, everything's just going to give me 0 because all of those terms have t in them. And in the end, this is going to simplify down to 18. Now, since we're doing this in sort of an application setting, you can see that if I integrate the velocity function, that's going to give me my displacement. So that's essentially my change in position over that time interval 0 to 6. Okay, so let's take a look at the graph over here on the right and just compare what we just found to what that actually means. So there's two ways to interpret that integral. So we have the velocity function plotted here, which was the quadratic that's on that graph, and then we have the position function, which is obviously the cubic graph that's shown there. So let's start with the position function. So if I were to get the position at time 0, you would see that the position at time 0 is down here, and then the position at time is equal to 6 would be up here. And what we just found is the change in position over that time interval 0 to 6. So if I were to take the position at time 6, subtract away the position at time 0, I would get 18. The other way we could interpret that same thing is to look at this velocity graph and get the area underneath that velocity graph all the way up to 6. So if I were to get the area of this rectangle, that blue shaded region there would represent the same thing that the integral found, which again is our change in position. So in the end here, we have two ways of looking at this. Now, I looked at this by actually taking an antiderivative using the fundamental theorem of calculus. Let's look at this in another way. So another way to interpret this is down here. It says, using the fundamental theorem of calculus, show that the integral can also be found using position at time 6 minus position at time 0. And what does that mean in this situation? Well, look at our position function. 1/6 t cubed minus t squared plus 3t minus 3 halves. And look at the antiderivative that I used when I solved this integral. Those are not exactly the same, right? The position function has a minus 3 halves there, and the antiderivative that I found in my solution there, my constant value was 0. But in the end, I want to show you here that you'll actually get the same thing regardless of which way you do this. So if I were to do the integral of this velocity function and assume that that's the same as the position at time 6 minus the position at time 0, well, now I'm using that position function. So most of this looks the same. I have 1/6 times 6 cubed minus 6 squared plus 3 times 6. Oops, 3 times 6. And then I have minus 3 halves. So that's my position at time 6. But now when I plug in my position at time 0, that's going to be negative 3 halves. And notice what happens here. So these two terms, I have a minus 3 halves, I have minus a negative. Those two terms are going to cancel out. That was sort of like my plus c term. In the end, I still get 18. So it doesn't matter what that constant value is when I do an antiderivative at the upper limit minus an antiderivative at the lower limit. I can have a plus c there, or I can, assume that that c value is 0. It's not going to make a difference. And that's really what we're showing here is, the solution that I got when I worked it out the first time, I got 18. I assumed that the plus c was 0. And then the second time I used that actual given position function and had a c value of negative 3 halves, and I still got the same result. So the main thing is the plus c doesn't make a difference. That's why we don't write the plus c when we do the definite integrals, and that is why when the fundamental theorem of calculus says any antiderivative, it's because all of the terms with a t are going to be the same. The only thing that changes to make it from a single antiderivative into any antiderivative is that then we have a plus c there. Okay, so now we have this next piece here. It says, what would the following integrals represent? Okay, so now that we know we're integrating velocity functions, we're going to assume v of t is velocity function. Then what I'm looking at on each one of these is just the displacement of whatever this is on the interval for the first one from 1 to 4, on the time interval from 0 to 3, on the second one, and on the time interval from 5 to 6 for the third one. So that's really the main idea. Now, one thing you can do when you're using problem-solving scenarios with these integrals is you can think about units. So take a look at the velocity function, right? Let's assume our velocity is in meters per second. Well, the dt part of this is a time measurement. It's going to really, really small time interval, but that would be measured in seconds. If I were to multiply velocity times dt, meters per second times seconds, it's going to give me meters. So we can always kind of tell if we have these things set up correctly. Essentially what we're doing here is we're integrating a rate function. The rate of change of the position is v of t. And when I integrate that, it's giving me my net change in the position. So I would expect my answer to be in meters. And you can see that for every, if I think of this as a rectangular approximation, for every rectangle, I would have meters per second times seconds. And in the end, I would have a bunch of rectangles that represented total amount of meters. So you can use units to make sure that your setup makes sense when you start using integrals and applications. Okay, so here's another example. Now, what we're going to do primarily here today is we're going to look at a lot of different types of fundamental theorem of calculus questions that you might see, just to make sure you kind of understand the main idea behind it. For this one, it says the graph of the function is given, and g of x is an antiderivative of f. If g of 3 is equal to 4, find g of 0. Okay, so anytime we look at these problems, and I gave you a worksheet at the end of this set of notes. Anytime you look at these problems, if you always remember what that second part of the fundamental theorem of calculus says, this becomes very, very simple. So we're talking about integrating the f function. Okay, so if I were to integrate the f function from 0 to 3, that would give me, assuming g is an antiderivative, that would give me g of 3 minus g at 0. Now, noting that I have this idea from the second part of the fundamental theorem of calculus, I can now just think about, okay, what parts of this do I know and what parts of this can I find? Well, looking at the graph, I can get the integral from 0 to 3 of f of x dx because I've got this graph to work off of. So that is, I'm just going to put a check here. That's a quantity that I can find, or at least I know it or I can find it. Okay, and then I also know what g of 3 is, and they asked us to find g of 0. So I essentially have a really simple equation. I'm looking for g at 0, and then I can just kind of go through and solve for the part that I need. If I were to get the integral from 0 to 3 of f of x, we can use the areas of those triangles there. We would find that the integral is actually 3/2. We were given the fact that g of 3 is equal to 4, and the only unknown I have here is g of 0, and from that I can get the g function at 0 would have to have a value of 5/2. So you'll be given a lot of different problems when you work through the fundamental theorem of calculus assignments that you have. And if you always remember that main idea, that's going to take care of the vast majority of those types of problems. It's just understanding what the fundamental theorem of calculus says. Now, here's another example that's just intended to be done with a calculator. It says the velocity of a car traveling down a straight road on the time interval 0 to 8 seconds is modeled by the function natural log of t plus 1 plus 20 meters per second. The position of the car is being measured from a fixed point along the road. If the car is 50 meters from the measuring point at time is equal to 6 seconds, what was the position at time is equal to 1? Okay, so remember again, we're talking about position, we're talking about velocity. Well, how can I relate these things together? Well, I know if I were to integrate my velocity function, here's my velocity function. It's already defined up above, so I'm not going to rewrite it. But my velocity function, I'm looking at the position at time is 6 and the position at time is 1. Well, if I were to integrate this from 1 to 6, I know I would have the position at time 6 minus the position at time 1 because integrating the velocity function is giving me the displacement. So in the end, this is actually just like the problem that was up above. We can use the calculator to get the integral from 1 to 6. We know what the position at time 6 is. It was 50. And then we can solve for the position at time 1. So it turns out the position at time 1 is about negative 57.235 meters. And again, that's all based on the idea that I can find the integral using the calculator. And the fundamental theorem of calculus tells me that the integral of the velocity function is related to the change of the position in this manner. Okay, so the first part of the fundamental theorem of calculus had to do with the idea that a derivative and an integral are inverse operations. So this is actually a really, really simple idea, but I'm going to show you this a couple of different ways. So there's a shortcut for the process when we take the derivative of an integral, but I first want to work this out all the way through so you can kind of see what they're talking about when they're essentially telling you that these are inverse operations. So I'm taking the derivative of the result of the integral from 4 to x of t cubed dt. Well, let's just go through that process. If I were to solve this out, I'm taking the derivative, antiderivative of t cubed is t to the 4th over 4. And I'm going to evaluate that from 4 to x. Okay, so let's actually plug into this. So if I were to plug in my upper limit and my lower limit into my antiderivative here, I would end up with x to the 4th over 4 minus 4 to the 4th over 4. Okay, so now we've solved the integral. Now let's take the derivative of the result, which is what we were intending to do. Well, the derivative with respect to x of x to the 4th over 4 is just going to give me x cubed when I do my power rule. And the derivative of 4 to the 4th over 4, that's the derivative of a constant. So in the end, I just get x cubed. So notice that we started with this function t cubed, and all we really did was replace the variable there, right? We just changed the variable from a t to an x, because essentially what happened here was those two operations essentially canceled themselves out. Okay, so let's take a look at another question here. So the nice thing about this is, once I know how this works, I don't really have to work through these integrals every time, because if I know what's going to happen, there's really no reason to work through this whole process. I'm going to show you this one more time the long way, and then I'll show you how we can just shortcut this process. So here we're taking the derivative with respect to x, the integral from negative pi to x of cosine t dt. Well, if I were to take the antiderivative here, you can see that the antiderivative of cosine is sine, and we would evaluate that from negative pi to x. So in the end here, I'm taking the derivative with respect to x of the sine of x minus the sine of negative pi. Okay, sine of negative pi is a constant. It is 0. I don't really care about that. What I do care about is the fact that if I take the derivative with respect to x of it, derivative with respect to x of sine x is cosine x, and the derivative of the second part, derivative of a constant, is 0. So I'm just going to end up with cosine x. So again, notice that all we really did here was essentially replace the t with an x. Okay, so here's another example. We have the derivative with respect to x of the integral from 2 to x of 1 over 1 plus t squared dt. And what I want you to do is just take a second and try this one. Okay, so hopefully you saw fairly quickly here that the solution should just be 1 over 1 plus x squared. Now, if we really wanted to, we could take the antiderivative, get an inverse tangent, and then plug everything in, take the derivative of the inverse tangent, give us 1 over 1 plus x squared. But the idea here is to recognize that these are inverse operations, and that's not necessary. So what we're trying to do is understand that inverse operations are being done here, so there's no reason to work out the process in that manner. Now, where these can get a little tricky is when you have limits of integration that don't just involve x. So we've got one worked out here where essentially what I've done here is try to show you this by converting what we have into the same form as what we were just using. So we have y is equal to the integral from 1 to x squared of cosine t dt, and we want to find dy dx. So essentially we want to take the derivative of that integral. Well, with the x squared there, it throws things off a little bit. So we're going to do just a simple substitution here. We're going to say, okay, instead of using x squared, let's just say that our u is x squared. So now this integral becomes the integral from 1 to u of cosine t dt, and we know u is x squared. Well, following through then with our chain rule, if we take the dy du and multiply times du dx, that would mean that these du's cancel out, and I would get dy dx, which is what I want. Well, take a look at what we've got here. If I take the derivative with respect to u of the integral from 1 to u of cosine t dt, that's going to give me cosine u. Du dx, well, u was x squared, so du dx is just 2x. So we have that piece. And so in the end, we just get 2x times the cosine of x squared. Okay, so the main idea there is there's chain rule involved, because if I actually did the antiderivative, then what would happen when I take the derivative is that the chain rule would come into play. And so let me show you kind of the other way of solving this out. If we were to solve this integral, this is essentially saying evaluate the sine of t from 1 to x squared. This is what y is equal to, which is the same as sine of x squared minus the sine of 1. Well, now when we take the derivative of that, derivative of sine is cosine, derivative of x squared is 2x, and that's going to give me the 2x cosine x squared that I got before. So again, we're kind of trying to bypass that whole antiderivative process, understanding that these are inverse operations. Okay, so here's another example of that. And I just want you to think about, okay, in addition to plugging in the 5x for the u, what else would you have to do to this? Okay, so hopefully you're seeing that this would just end up as the square root of 1 plus 5x squared over 5x, and then we have to multiply by the derivative of the 5x, which would just be 5. Okay, so that's really the main thing, is that the chain rule comes into play by us needed to take the derivative of that limit of integration, because we would have taken the antiderivative and then the derivative. Okay, so it's fairly simple once you wrap your head around it. Now here's another example. We've got an integral from x to 5, 3t sine t dt. And notice that our limit of integration here is the lower limit of, the limit of integration that is a variable this time is the lower limit of integration. So with that being the case, if you think through the antiderivative process, we would have the antiderivative at 5 minus the antiderivative at x. What that tells me is that my result is going to be negative, and I would just have negative 3x sine x, because this time it would have been the second term in the antiderivative process, or the fundamental theorem of calculus process for solving a definite integral. It would have been that second term that I would have been taking the derivative of, and that's why it's negative. Okay, so again, fairly simple once you understand how these work. Okay, so here's a few more examples that I want you to try. So there's 3 of them here, and what I want you to do is just pause the video, and when you come back, I'll show you the solutions to these. Okay, so here are the answers that you should have come up with. You can see on this first one, we've got a lower limit that has an x in it, lower limit of 3x squared. So I know it's going to be negative, first of all, because when I take the derivative of the upper limit, it's going to give me 0. So I'm going to subtract away the antiderivative with the 3x squared plugged in it, and then take the derivative of that. So that's going to give me a negative. And then also, don't forget that we have to do the chain rule here, because our limit of integration is not just an x. We actually have 3x squared here. So that's where the 6x came from, is just using the chain rule. Okay, so fairly simple. Second one, the difference here is we have an upper limit of integration that has an x in it and a lower limit that has an x in it. So if I were to think through the process here, I would have my antiderivative at the upper limit minus the antiderivative at the lower limit. This time then, when I take the derivative, neither term's going to become 0. So I'm going to end up with the chain rule for both parts of it. And you can see that this piece of it was just working with the upper limit, and then I'm subtracting away this part of it because it was the lower limit. And again, the 2x came from the derivative of x squared. The 2 over here was the derivative of 2x. Okay, so fairly simple again. All right, and then the last one, same idea. We have an x in the upper limit and an x in the lower limit. So same process. We could actually work this one out the long way if we wanted to, but really not necessary. I know I'm going to get cosine squared x times the derivative of cosine minus sine squared x times the derivative of sine. Okay, so in the end, that's the result that we get. Okay, so for this next part, we're looking at functions defined by integrals. And when we talk about a function defined by an integral, this is actually something we're going to get into a lot of applications with next time. We're going to spend a second day on the fundamental theorem of calculus. But the idea here is that you can't always find the antiderivative of your function. So for example, here, we've got this derivative, square root of 3 minus cosine x. And we're trying to find the original function if it goes to the point negative 3, 4. Well, since I can't take the antiderivative of square root of 3 minus cosine x, what we're going to do is use this form for our solution. And it's pretty simple once you wrap your head around this. I'll explain what's going on here. So first of all, we're going to take the integral of our derivative just like we normally would. But the one thing I'm going to change is I'm going to use what's called a dummy variable. And a dummy variable is just something that's sort of a placeholder. And the reason that's important is because we're going to integrate, just like it shows here, from a to x. And a is going to be the point that we know our function needs to go through. So it's going to go through x is negative 3. My upper limit is x. And now to get the function to go through the point y is equal to 4, let's think about what would happen here. If I plugged negative 3 into this function right now, if I did y of negative 3, I would end up with an integral that went from negative 3 to negative 3, which would give me an integral value of 0. And I need, when negative 3 is plugged in, I need this function to go through a y value of 4. So in the end, this is what we end up with as our function defined by an integral. Notice if we took the derivative of this, we would get the square root of 3 minus cosine x. And if I plug negative 3 in, I do get a y value of 4. So even though we couldn't actually solve the integral and get the true y function in the traditional sense, we still could get our function in terms of an integral. Okay, so I want you to try this next one. We have dy dx is tangent x, and we have f of 3 is equal to 5. So just pause the video, and when you come back, I'll show you the solution. Okay, so when you work this out, it's really the same idea as the last one, right? We've got the integral from 3 to x of tangent t dt. If I take the derivative of that integral, I am going to get tangent x. And now I need to make it go through the 0.35. I've chosen my lower limit to be 3 so that when I plug in 3 for x, that makes that integral 0. And then I can add 5 to make it go through the 0.35. Okay, so we'll do some more stuff with functions defined by integrals next time, but I just wanted you to see the beginning of that so you can understand how it works. Last thing here, I want you to try one more integral here. And this is stuff that we did back in section 6.3. Now that we've talked about the fundamental theorem of calculus, you kind of understand everything behind it. But what I want you to do is try to solve this one, not because it's anything new, but just because I want to emphasize a couple of things about when you solve these, things with notation and things to be very, very careful about. So pause the video, solve that out. When you come back, I'll show you the solution. Okay, so here's the solution that you should have come up with. Now, the big thing that I want to note here, I think everybody knows how to do the antiderivative at this point. You understand that it's the antiderivative at the upper limit minus the antiderivative at the lower limit. We've been doing that for a couple of weeks now. But where people tend to make a mistake is when they actually plug in these values. So if you notice here, this is everything with, that's my antiderivative with 3 plugged in. I'm subtracting away my antiderivative with -1 plugged in. Now, notice I have the brackets around all of those terms. That's reminding me that it's the antiderivative at the upper limit minus that same antiderivative evaluated at the lower limit. So I have to subtract all of those terms. So either with parentheses or brackets, I always write it out this way so that I don't make any mistakes with things like subtracting a negative. It's very, very easy to mess things like that up. Okay, so that's the first thing. The second thing is when you get into a situation like this where you have a lot of different denominators, you might think immediately of getting a denominator of, let's say here, a denominator of 12 because it looks like the common denominator between all those terms is 12. Well, that's usually not going to be your most efficient way to do this. The best way to go about this is actually to go through and try to combine what you can first. So for example, all of the expressions that have a denominator of 4, combine those together, you get 80 over 4. When I go through and I look at the constant terms, I have a 9 plus 3 minus a -1. So 9 plus 3 was 12, minus a -1 was plus 1. Essentially, that's 13. And then I have a plus 1/3. Now, when I start simplifying through this, 80 over 4 is 20, plus 12 plus 1 gives me 33, plus a 1/3. Well, now I can get a common denominator, and I only had to do it one time on one term. I had to get a denominator of 3, and you can see we end up with a result of 100 over 3. So not really anything difficult in here, just the idea that you can save yourself some time if you really try to group things together in the right way. A lot of times these denominators will take care of themselves, and you won't have to just blindly get a common denominator with all of your terms. So I bring that up because since we're covering the fundamental theorem of calculus, and especially with that first part that we discussed with the antiderivatives, this idea of solving an integral using antiderivatives will show up within your assignment, and you might see some with fractions like this. So I want to make sure everybody's really clear on what to do when you see those types of problems. Okay, so you do have an assignment in Math Excel. In addition to that, I also attached a worksheet here. And I attached a worksheet because what's in Math Excel, they're good questions. They tend to be very repetitive though, and they don't necessarily give you the types of questions that you might see down the road on your AP exam. So what I tried to include on this worksheet were questions that were more along the lines of like, AP style questions. So you've got different questions here. Some of these are just derivatives of integrals, which is pretty straightforward. But if you look at number 4, you can see we're starting to interpret using the fundamental theorem of calculus. We saw a question like number 5 back in the notes. And then this is where we actually have on number 6 a function defined by an integral. I want you to try that one. We'll talk about that one in class. But then when you look at things like the second part where we're on the calculator part, well, take a look at number 2. a car sold for $16,000 and depreciated at a rate of 2e to the x squared dollars per year. What is the value of the car 3 years after purchase? Well, that's not obviously a fundamental theorem of calculus question. We're more in an application problem where we have to understand the relationships between a rate function and how that's going to relate to the information that we're given there. So make sure you try some of these because, like I said, they're formatted in a little bit different way. Take a look at number 5 again, another example here. We're given h of x, we're given g of t. They say find h double prime at 2.5. Notice that h is defined as the integral of g of t. So again, a little bit different type of question than what you're going to see in the homework. So make sure you practice with some of these because they are going to give you some problems here that are going to work a little differently than the stuff that you see in Math Excel. Okay, so we'll talk about some of those next time in class. But in the meantime, work on that Math Excel assignment and at least try some of these on the worksheet.